Right, so last time we took a look at graphing sine and cosine. This week we're going to kind of step back from doing the graphing and the visual stuff and focus more just on more the algebra side. Right, so we're going to look at what are called trig functions of an acute angle, which basically means we're going to be using right triangles. Okay, does anybody remember what a right triangle is? Bless you. Yeah, it's a triangle that has a right angle or a 90-degree angle. Okay, every problem that we do with a triangle this week, it's going to be a right triangle. Okay, what do we call the side that's opposite the right angle? It's the longest side in a triangle. It's your hypotenuse. And what about the two sides that are not the hypotenuse?
The legs.
The legs. Okay. When we have legs, one we usually call opposite, one we call adjacent. We'll get to that in a second. Okay, so here's everything we just said as a diagram. Here's my right triangle. I've got my 90-degree angle, which we put in that little symbol. Kind of looks like a little box in the corner. The sides we usually label with letters A, B, and C. Okay, A and B are the legs. It doesn't really matter which one's A and which one's B, but we usually just make sure C is always the hypotenuse. Okay, and I've written here that this is an acute angle. Okay, theta is an acute angle. How come? Why can't it be bigger than 90?
Then it's going to be smooth or something.
All right, so if it was bigger than 90, it would be an obtuse angle. What's wrong with that? Why can't you have an obtuse angle in a right triangle? Yep.
You have three angles, you already have a 90 degree, you need two more angles at 90 degrees, or one angle would not leave any more to be the other angle.
Right. So the key here is all the angles add up to 180. So if all the angles are going to add up to 180, okay, we got to make sure that the other two angles are less than 90. Okay, they have to be acute. Okay, there's a theorem that we can use, okay, with right triangles called the Pythagorean Theorem. And can anybody explain to me? You can either use letters or actually just explain what the actual theorem is. If you use the letters, and then I'm going to ask you what that means. Yeah.
Well, like I do it in shop optical corners, and it's like one side of the wall is 3 feet, the other one's 4. And if you do it correctly, to the point where you ended from 3 and 4 should equal 5.
Yeah. So what Kyle's saying is you can use it to check if something's square, like if you're building like a foundation. So if you had, pretend like this is a top-down view of like a foundation or framing something. If you measure out 3 feet on one side of the foundation, okay, 4 feet on the other, when you measure that distance across, it should be exactly 5 feet. If it's not, then this angle right here is not square. It's not 90. And you could do the same thing on a bigger scale. You could measure 30 feet, 40 feet, and the diagonal should be 50 feet. Okay, that would be better for a foundation that's bigger. But yep, so you can use it for that. But what is the theorem itself? Like if we're going to fill in numbers and we're going to use it, yeah.
A squared plus B squared equals C squared.
Right, so A squared plus B squared equals C squared, which means if you take one leg and square it, take the other leg and square it, and then add those together, it equals the hypotenuse squared. And maybe if we have time, we can see why that trick works when you plug in a 3 and a 4 and get a 5. Okay, and there's a special name for that, which, again, we'll probably get to in a little bit. All right, so any questions on that? All right, so keep this theorem in mind as we start to solve right triangles. All right, so before we defined our 6 trig functions on a unit circle. Okay, so we used x's, y's, and that was pretty much all we needed. Well, now we're going to switch over to using the terms opposite, adjacent, and hypotenuse. And I'll show you in a second that the way we're doing it now and the way we did it before, same thing. Okay, just like a different way of looking at it. Okay, so here's our first 3 trig functions in terms of the words opposite, adjacent, and hypotenuse. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now hypotenuse, that's pretty straightforward. Hypotenuse is always the side across from the 90. It's the longest side in the triangle. But opposite and adjacent, okay, those are what we call relative terms. Okay, I'll show you what I mean by that. Okay, opposite and adjacent are relative terms. Okay, they're kind of like left and right. Okay, which side is left and which side is right, it depends on which way I'm facing. Okay, if I'm facing you guys, left is the door, right is the windows. Right? But if you're facing me, that's switched. All right? So it's all relative to wherever you put theta. Okay, so you pretend like you're standing right there. Opposite is what's farthest away. Okay, adjacent is the side that's right next to it. All right? If you change where you're standing, okay, what that does is it switches opposite and adjacent. So if we decide to put our angle up here instead, now opposite is what's farthest away, and adjacent is what's right next to it. Okay, so any questions on that? Okay, so opposite and adjacent can switch places, just like left and right switch, okay, depending on where you're standing. All right, and does anyone remember when we did unit circle trig, what we do to each one of these? To get those straight? Yeah, we just flip them. Okay, so your cosecant is hypotenuse over opposite. Your secant is hypotenuse over adjacent. And your cotangent is adjacent over opposite. Right, so now when we did unit circle, we didn't use these words. We used x's and y's. So does anybody remember which letter sine was equal to when we did unit circle?
What letter?
Yeah, out of the 2 that I just mentioned.
Y?
Y. Yep, sine is y. And cosine was x. And how did we get the
I think it's X or Y.
Y over X.
y over x? It's like you just take the 2 that are right there and you just divide them. Y over x. Well, this is exactly the same thing as what we just wrote. Okay? If you look at this diagram, let's just make our unit circle. Okay, I'll put a point somewhere on it. I'm going to make a triangle. I'm going to put theta right there. Okay, I'm going to call this side x and that side y. And that coordinate, I'm just going to call xy. Okay, it could be any 2 numbers. Right. Let's use this definition and see what we get. So Derek, sine is opposite over hypotenuse. What side is opposite theta here?
Y.
Y. And do you remember how long the hypotenuse is in a unit circle?
1.
1. And what's y divided by 1?
Y.
Yeah, just y. So using opposite over hypotenuse, we get exactly what we did with unit circle trig. I just never explained it that way. Okay, cosine is adjacent over hypotenuse. So Tyler, what side is adjacent to theta?
I can't really.
You need a little bigger. So what side is adjacent to theta? No, y is opposite. Opposite's always the side that's farthest away. No, hypotenuse, adjacent means right next to it. So what's the side that's right next to theta? You want to help him out, Dalton?
X.
Yeah, x. Okay, x is adjacent, right? Hypotenuse is 1. Plug them into that formula for cosine, look what you get. Adjacent is x, hypotenuse is 1. X divided by 1, there's x. Okay, same definition we had before. We didn't explain it in terms of the words opposite and adjacent. Okay, and last one is y over x. Well, let's see how we get that. Okay, opposite over adjacent. That's a what side is opposite theta? Y. What side is adjacent? X. Y divided by x, opposite over adjacent. That's where that one comes from. Okay, so now that we understand, or starting to understand, right triangle trig, we can kind of see where these came from originally. Okay. Right, so any questions on these 6 definitions or on the words opposite and adjacent? All right, so what we're going to look at here is basically, does the size of the triangle matter? For example, if I find I don't know, let's say the sine of 30 in a small triangle, or I find it in a big triangle, does it make a difference? Okay, and the answer is no. Okay, trig functions always have the same answer. It doesn't matter the size of the triangle you're working with. All right? These are called similar triangles. Okay, remember, similar means that one is an enlargement of the or reduction of the other. Okay. Right, so let's try. Let's find the sine of 30 here. See what we get. Then we'll find the sine of 30 over there, and I'll show you they come out the same. So Tyler, what's sine again? What 2 sides do we use?
Opposite and hypotenuse.
Opposite and hypotenuse. Yep. What side is opposite to 30? 1. And what's the hypotenuse? 2. That's it. That's the sine of 30. 1/2. Okay. Now let's do it in the big triangle. Okay, Upi, what side is opposite 30?
2.
And the hypotenuse? Is that the same thing? Yeah, it just reduces to 1/2. Okay, so the point doesn't matter the size triangle you're using. Okay. Sine of 30 is always 1/2. Any questions on that? All right, so now let's say I just gave you this piece of information. I said to you the sine of 30 is 1/2. Find everything else. Find the cosine, find the tangent, find the secant, the cosecant, and the cotangent. Well, this is all you need. As long as they give you one of the trig functions, you can find everything else you want. Right? So the first thing we're going to do is take what you're given, and we're going to use it to label 2 sides of a triangle. So in the case of sine, you know the opposite, and you know the hypotenuse. It doesn't matter if it was a bigger triangle and it was reduced. Size of triangle doesn't matter. All right, so they'll give you a trig function. Label the 2 sides. And then if you know 2 out of 3 sides in a triangle, use the Pythagorean Theorem. Okay, then you can get the 3rd side. Okay, once you have all 3 sides, then you can find anything you want. All right, so the key is use the trig function they give you to label 2 sides. Then use the Pythagorean theorem to get the 3rd side. Now you can find any trig function you want. Right, so example 1a, they're telling us that the sine of theta is 5/6. It doesn't matter how you draw your right triangle. You can reflect it, flip it. That doesn't matter. All right, so Brendan, if they're telling me the sine is 5/6, what two sides do I know?
The opposite and hypotenuse?
Yes, I know the opposite, and I know the hypotenuse. Now, at this point, I can tell where hypotenuse is. Okay, that's always across from the 90. But what do I have to do to figure out where opposite is? Just looking at this top diagram, you couldn't say where opposite is yet.
I'm gonna say it's across from one of the 90 angles, or it's like,
Well, opposite the 90, what side is that?
so it'll be,
Opposite your 90 is always your hypotenuse. Okay, so that's the only side I know for sure right now. So what do I have to do to figure out where opposite and adjacent go? Yeah?
Have to figure out where theta is.
Yeah, I have to put theta somewhere. It doesn't matter where you put it. You can put it anywhere you want. Okay, so let's just put it at the top. Now that I made that decision, I know where opposite is and I know where adjacent is. Okay, Fernando, where's opposite in this triangle?
No, I mean,
Nope, the hypotenuse. This is the hypotenuse. Yeah, the one on the bottom. Okay, opposite is the side that's farthest away from the angle. It's the side that, if you got rid of it, you'd still have that angle right there. All right, so we got the opposite side as 5. And Matt, what's my hypotenuse? 6. Okay, now if we want to be able to find all 6 trig functions, I got to know that third side. So Paige, how do I figure this out?
The Pythagorean Theorem.
Yeah, just use the Pythagorean Theorem. Okay. If you want, call it A. And now solve for A. All right, so Cameron, can you give me my Pythagorean Theorem using what I got up here?
A squared plus 5 squared equals 6 squared.
Yep. So A squared plus 5 squared equals 6 squared. So A squared is going to equal 36. And I'm going to move the 25 to the other side. So John, what's 36 minus 25? 11. And then A is the square root of 11. Unless they ask for a decimal, don't worry about it. Just leave it like that. Okay, any questions on that? All right, so now let's write down our other trig functions. Okay, Brian, can you tell me what my cosine would be?
Square root of 11 over 6.
Perfect. That's it. Okay. Now that's not the angle. Okay, we didn't actually find how big of an angle this is. All we did was find the cosine of that angle. Okay, we're not going to worry about finding the actual angle till tomorrow. Okay, and my tangent. Oh, Kyle, what's my tangent?
5 over square root of 11.
Good. 5 over square root of 11.
I forgot what it's called.
Okay, I like that answer. There's only one thing we need to fix with it, but this is a good first step. What do I need to fix there?
Square root can be in
Right, we got to fix that square root from being on the bottom. Okay, I think we've done that before. Do you remember how to fix that, Amanda?
Yeah, you multiply the top and the bottom by the square root of 11.
Yep. And now in the top, that's 5 square root of 11 over 11. Okay, you do need to do that. Okay, anytime you get a square root in the bottom, just make sure you fix it. All right, so that's my cosine, that's my tangent. What else we got? Let's do my cosecant. Okay, cosecant, we could have done that one right away. How do you get cosecant very quickly if you know the sign?
Flip it.
Yeah, just flip it. So your cosecant is 6/5. So in fact, if all they wanted was the cosecant, you wouldn't even need the Pythagorean theorem. Okay, the only reason I needed it is because they want all of them, not just cosecant. Bless you. Okay, what about my secant? Can anybody give me that one and fix anything you need to fix? Yep.
It's square root of 7 over 6. I mean 11.
Yep. So it's going to be your cosine flipped. So it's going to be 6 over the square root of 11. So it's going to be just like tangent. You're going to have to fix it the same way. And lastly, my cotangent. Well, there's two things I could flip for cotangent. I could either flip my final answer for tangent, or I could flip what I had started with. Which one do you think is better to flip?
But
Which one?
I've always started them.
Yeah, why do you think that one's better to flip?
Maybe we don't have to deal with the square root of them.
Right, if you flip the first one, what's going to happen is the square root goes to the top, you don't need to fix it. If you take your final answer and flip it, you're going to have to go through all the work of fixing it again to get the same exact thing. All right, so I would just do that and you're done. Okay, so any questions on that? Okay, you're just finding the 5 trig functions. You're not actually finding the angle, right? Okay, sometimes the way I describe what we're doing, I've probably said this before, but it's like if you met somebody on the street and somebody said, describe some things about them. You don't need to know their name to describe things about them. Okay? So think of all these things as describing things about the angle. Okay, we know it's cosine, we know it's cosecant, we know a bunch of stuff about it, but we don't even actually know the size of the angle. And we don't need to. Okay, that's not what we're doing today. All right. This one's going to kind of get at an idea Kyle mentioned a little bit earlier. Does anybody know what the hypotenuse is in this triangle? Comes out, yeah, it comes out nice. It is 13. Okay, if you go through the Pythagorean theorem, you'll get that. And this is called a Pythagorean triple. Okay, a Pythagorean triple is a triangle where all the sides are integers, no decimals. Okay, 3, 4, 5 is one that Kyle mentioned. But you could also do this. Okay, if you wanted to check if your foundation or your frame was square, you could measure out 5 feet on one side, 12 feet on the other, and the diagonal should be 13. Okay, bless you. My guess in carpentry why they don't use this is, well, maybe it's harder to remember. 5, 12, 13. 3, 4, 5 is easier. Okay, but that's a Pythagorean triple. So what's nice about a Pythagorean triple is there's no square roots. So when we go through it, there's nothing here you need to fix. Let's start with my sine. Shannon, what's my sine here?
5 over 13.
Yep. Opposite over hypotenuse, 5 over 13. Okay, my cosine, how about Will?
Over 13.
Yep. So there's my cosine. And Fernando, my tangent?
5 over 12.
Good. 5 over 12. Any one of these pieces of information is enough if I actually wanted to find out how big of an angle is that. I could use any of those to figure that out. Okay, Brendan, what about my cosecant?
13 over 12, 15 over 5.
Yeah, 13 over 5. Jill, my secant?
13 over 12.
13 over 12. Cheryl, my cotangent?
5
Well, a hint is if we already have the tangent, just flip it. Yeah. And that's it. Okay, so those are my 6 trig functions. Chances are I wouldn't ask you for all 6 in one problem. This would be 6 separate problems on the test. Okay, so I'm not going to ask you to probably do that many. Any questions on that? All right. All right, so there's a couple angles that come up more than others. Okay, one is 45-degree angles come up a lot, and 30 and 60-degree come up a lot. All right, so it's going to be helpful if after a certain point we can kind of just off the top of our head know what's the tangent of 45, what's the sine of 45. Okay, so those are good ones to know. So we're going to go through all those right now. Okay. All right, so if I wanted to find all 6 trig functions here, the only thing I'm missing is my hypotenuse. Anybody tell me the hypotenuse there? Yep. Yeah, it's just the square root of 2. Okay, Pythagorean Theorem, 1 squared plus 1 squared, that's 2. And then take the square root. Okay, now we're going to do the same thing we just did. Okay, just go through the trig functions. Except the only difference this time is you actually know the angle. Not that we need to, but I want you to know this one. All right. As far as opposite and adjacent, it doesn't matter if you stand here or stand here. They're the same. Okay, use either one you want. All right, so Pat, what's my sine of 45?
1.
So sine is opposite over what side?
Adjacent. Or no, yeah, opposite over adjacent.
Let's see.
Oh, hypotenuse.
Hypotenuse.
So it'd be 1 over 2 squared.
1 over square root of 2.
Yeah.
Okay, and then when we fix it, it becomes square root of 2 over 2. Okay, Derek, what about my cosine of 45?
Is 1 over the square root of 2.
1 over the square root of 2, it's the same thing. The reason sine and cosine are the same is because opposite and adjacent are the same.
Is it the square root of 2?
So we got to get rid of that square root from the bottom. So you multiply top and bottom by square root 2. Okay, so in the top you get square root 2. In the bottom you get square root 4, or just 2. And Amanda, what's my tangent of 45?
Square root 2 over 2.
It's going to be
Well, it's going to be opposite divided by adjacent.
So just
1. Opposite, adjacent. Okay. So Paige, if my tangent is 1, that means my cotangent is 1. Okay, they'll stay the same. And my secant and cosecant are also the same. What is the secant and cosecant?
Square root of 2.
Yeah, they're both the square root of 2. Okay, how do you get that?
You just flip it. Square root of 2.
Yeah, just take what you had originally before you fixed it and flip it. Okay, so those are the 6 trig functions for 45 degrees. And those never change. Okay, no matter what problem we do, what size triangle, these are always the same. Right, so the last special triangle we need to look at is the ones that we have 30s and 60s. Okay, and I'm giving you a hint at how to start. It doesn't matter if I use sides of 2, 2, 2, 7, 7, 7. I just need to start with an equilateral triangle. How come? What do we know about the angles in an equilateral triangle? They're all the same. So what does that mean?
All the sides are the same.
All the sides are the same? Do I know anything more specific about the angles?
They're all 60.
They're all 60. That's why I decided to use an equilateral triangle. So somehow here I can create a 30. I have to add a line. Does anybody see where I could add a line here? And it would give me a 30, a 60, and a 90. Yep.
Straight down the middle.
Yeah, just put a line straight down the middle. Okay, we're not going to get into the geometry of why that is, but this is an angle bisector, and it's also a segment bisector.
Should be on the both side or one side?
What's that?
Should be on the both sides or one side? The 90 degree.
Well, you get 90 on both, sure. Yep. Right, so now what I'm going to do is off to the side, I'm just going to look at half of this triangle. Just focus on the left half. So we know this side is 2. How about the bottom side? Yeah, it's 1. Again, we're not going to do the whole statement, reason, proof as to why this is an angle why it's a segment bisector, but it is. Okay, each side is 1. And that means this side would be 3.
You messed those up.
No, sorry, I messed that up. That side would be, what would that side be? Square root of 3. So if you square that side, you get 1. If you square that side, you get 3. 1 and 3 is 4. Square root of 4 is 2. Is that a Pythagorean triple? No. Okay, because one of the sides is a decimal. All right, so this was my 60. Okay, that's the original angle I had right there. And this angle at the top is my 30. What's nice about writing trig functions for 30 and 60 is it's the same triangle. Okay? All you're really doing when you switch your angle is you're switching your point of view, but it's the same sides. Right, so let's find, let's try the sine, the cosine, the tangent. If that goes well, then we'll stop with those 3 for 30. Okay, if you guys need some more practice, we can do the secant, the cosecant, and cotangent. Right, anyone tell me my sine of 30? Yep.
Square root of 3 over 3.
Remember we put theta, does it matter?
Yeah.
Well, this time it's 30, right?
So theta.
So that's our reference point, where the 30 is. Yep, 1/2. I think we did that a little earlier. Okay. Sine of 30, 1/2. Okay. How about my cosine? What's my cosine? Yeah, square root adjacent over hypotenuse. And what about my tangent? I think somebody said this one earlier.
1 over square root of 3.
1 over the square root of 3, which would fix
Square root of 3.
Square root of 3 over 3.
square root of 3 over 3. Okay, does anybody need me to go through the other 3, flipping them? Okay, so now let's just do it. We'll do the first 3 for 60. Sine, cosine, tangent. What's the only difference between a 30 and a 60?
Adjacent and opposite are switched.
Yeah, that's all that happens. Opposite and adjacent switch places. Okay, so what's my sine of 60? You keep in mind, you're now, pretend like you're standing in the bottom left angle. Yep.
Square root of 3 over 2.
Square root 3 over 2. Okay. What about my cosine of 60?
We start 3 over 2. 3.
So for cosine, you're looking at the adjacent and dividing by hypotenuse. 1/2. Okay. So everything is just going to switch places. This last one we're not going to see. The cotangent of 30 would have been the same as the tangent of 60. We didn't do the cotangent of 30 though. All right. So now my tangent of 60 is opposite over adjacent. Square root 3 over 1. Right. Any questions on those? Yeah, I think probably tomorrow, I'll give you guys a sheet that has all the angles that are multiples of 30 and 45 and all their trig functions. Okay. All right, so last thing we're going to look at is has to do with complementary angles. Okay, just as a reminder, complementary angles means they add up to 90. So I'm saying here that if the two acute angles in a right triangle are always complementary, how come? Why would the
They
two?
add up to 180.
All right, so let me write that down. Since all angles add up to 180, okay, yeah, keep going.
Doesn't the complementary make 180?
Where's the 90 coming from?
Half of 180.
The right angle. Right? So since all angles add up to 180, and we used 90 degrees for the right angle, the other two angles have to add up to 90, which means they're complementary. Other two angles must add to 90. It's almost common sense, but really, if you're going to spell it out and explain why, that's why. Right, so as we start to work more with right triangles, we need names for the angles. Okay, we already have names for the sides, A, B, and C. But these are the letters I'm going to use for angles. Okay, it's going to be a little different than the way your book does it. Does anybody remember what this one in the lower right's called? It looks like a fish.
Infinity.
What is it?
Infinity.
No, infinity, that would be that symbol, kind of like that. But that is a Greek letter.
Alpha.
Yeah, that's alpha. And notice I put alpha across from A. And does anybody know the Greek letter at the top? That's beta, and I put it across from B. It doesn't matter where you put A and B in terms of which leg is which. Just make sure you put alpha across from A. Make sure you put beta across from B. Okay? Now, our book does it a little different. Okay? They're going to use capital letters for the angles. Why do you think that could be a bad idea?
It was like S's are the same, Z's are the same.
Yeah, certain letters might look the same. So like capital C, lowercase c, you wouldn't be able to really tell the difference. The other thing is, if you asked me, well, I don't know how to find A, then I'd have to say, well, which capital A or small a? Okay, it's confusing. So in any problem in the book, if you see capital letters, those are angles. If you want to cross it out, not in the book, but on your homework, make it a Greek letter, I would probably do that. Okay, so here's our diagram we're going to use when we talk about triangles. All right, let's find a couple things here. Let's find the sine of alpha. Okay, there's not going to be any numbers here, so you're not going to have to worry about square roots, any of that stuff. It's just going to be 2 letters. John, can you tell me what side is opposite alpha?
A,
And what side is the hypotenuse?
C.
See? And that's it. That's the sine of alpha. Opposite over hypotenuse. Okay, let's find the cosine of beta. Okay, looking at same diagram, anyone think they can tell me the cosine of beta? What is it? It's A over C again. Yep. Adjacent over hypotenuse. Adjacent over hypotenuse. So what do you notice about sine of alpha, cosine beta? They're the same. Okay, we've already seen this idea with numbers before. Sine of 30, cosine of 60. Came out the same. Okay, let's do one more. Let's do tangent of alpha. What is it? Not any numbers here. It's all going to be letters. Let's see, opposite over adjacent, yep. A over B. Okay, now I want you to find cotangent, but use beta. So I'm looking for adjacent over opposite. So what side is adjacent to beta? A over B. Adjacent over opposite. Okay, so notice they came out the same again. Okay, and we could keep going with things that are going to come out the same. I could do the secant of alpha and the cosecant of beta. They'd be the same. Okay, and the reason they keep coming out the same is because it's a theorem. It's called the Complementary Angle Theorem. Okay, and the first part kind of tells you something it has to do with complementary angles. Okay, remember, we said that the 2 acute angles in a right triangle are complementary. Okay, so alpha and beta add up to 90. The other thing it has to do with, it's called cofunctions. Cofunctions is just another way to pair up trig functions. Okay. These are your cofunctions. Sine, cosine. Tangent, cotangent. And then secant and cosecant. All right, so it's a little different than the way we usually pair them so that they're reciprocals. You flip one to get the other. That is a way you can pair them. That's different. These are called cofunctions. You just take a trig function and put the word co in front of it. It just happens that tangent and cotangent, they pair up the same. They are reciprocals and they're cofunctions. Okay, but the other ones pair up a little differently. Sine, cosine, tangent, cotangent, and I didn't do the last one. Right, so this theorem basically says as long as you have 2 things, okay, they're going to come out the same. The 2 things you have to have, first of all, you have to have cofunctions. Right, tangent, cotangent, sine, cosine, secant, cosecant. So you have to have those 2 functions. And the other thing you have to have is complementary angles. And if we're working with a right triangle, we just said that they always are complementary. And that's it. That's the complementary angle theorem. Cofunctions of complementary angles come out the same. Right, so we're going to see if we can use that idea to simplify that. Okay, first I'm going to check if I can use that idea here. Cameron, do I have cofunctions here?
Yeah.
Yes, I do. Sine, cosine. Okay, so there's my cofunctions. Brendan, do I have complementary angles?
Yes.
Yes. If I take 35 and 55 and add them up, they add up to 90. So I have cofunctions. I have complementary angles. So what do I know about this and that?
They all add up to me.
They're what, Jamie? They're equal. Whatever the first thing I circled in green is, it's exactly equal to the second thing I circled. So what do you get when you subtract these two things? 0. That's it. Okay, and that only worked because I had cofunctions and complementary angles. Okay. What is the sine of 35? I have no idea. I don't know. It's some decimal that never ends. It goes on forever. What's the cosine of 55? I don't know. But what I do know is they're the same. So if I subtract two things that are the same, I always get 0. All right, let's try this one. Okay, very similar idea. Fernando, do I have cofunctions here? Yep. Tangent, cotangent. Okay, Will, do I have angles that add up to 90?
Yeah.
Yep. So now, what do I know about these two things? They're the same. They're cofunctions. They're complementary angles. So what am I going to get if I divide them? 1. Okay. I have no idea what the tangent of 20 is. I have no idea what the cotangent of 70 is, but I know they're the same. Divide two things that are the same, you always get 1. Okay, any questions on that? All right, and the last one. Similar to example B. Anyone think they can tell me what you get here and then tell me why that's what you get? Yep. Yep, you do get 5. Can you just explain how come?
So they're cofunctions.
These are cofunctions, yep.
It's going to be 1.
And those are complementary.
Yeah.
That's important too.
So it's going to be 1 times 2. That's 3.
Yeah. So what's in the parentheses is just a 1. As Jamie just said, times 2 is 2. 2 plus 3 is 5. That's it. All right, so it just gives you a trick to simplify some trig expressions in your head. Obviously, this is very special. Okay, if you change that 15 to a 14, then you need a calculator. Okay, so any questions on that? All right. All right, so I'm going to give you guys got about a little over 20 minutes. I'll give you some time to start the homework. Okay, it's on 361. I'd like you to try 1 to 14, 16, 18, 21 to 23, and try to simplify these two expressions. It's just like what we did at the end of class.